Hello AP Stats students, happy Tuesday. Mr. Hazelhorst here with you, here for you today with your second video over chapter 4. Today we're going to look at what's known as a power law model. Again, we're going to be utilizing logarithmic transformations and seeing what happens as we transform data using a different model. But again, ultimately you're going to see the same concepts from yesterday, the same concepts from chapter 3. So if anything, hopefully this just gives you some more practice on this whole big picture of transforming data. So let's begin with an example problem. If you want to go ahead and input all this data into your graphing calculator, we're going to input distance from the sun in list 1 and period of revolution in list 2. This is on page 282 in your textbook. You also should have a note sheet in front of you with this information. So feel free to go ahead and again get that input into your calculator. The reason why we're putting distance from the sun in list 1, it's representing our explanatory variable. The farther a planet is from the sun, we know the longer its period of revolution. So therefore, revolution is dependent on that distance from the sun. While you guys input those numbers into your graphing calculator, I'm also going to get on my soapbox real quick and make fun of science for a moment. When I was in school, and when this textbook was written, Pluto was still a planet. And then, like many great fallacies in science, they decided, oh, we made a mistake, and Pluto is no longer a planet. But for our purposes, Pluto still matters to us. Pluto is still important. We're including Pluto in the data, and we'll go from there. All right. So hopefully at this point you've got all that information input into your graphing calculator. And what we want to do here to begin with, let's create a scatter plot. So we'll pull out those graphing calculators. I have the data input into my graphing calculator. So we'll go ahead and set up our scatter plot. We got L1 and L2 ready to go here. So we hit zoom 9. And again, just like yesterday, we have a curved set of data. So since we have a curved set of data, let's just take a moment and let's do what we did yesterday. All right, yesterday we created an exponential model. And remember, we created an exponential model by applying the natural log, right? So let's do that here. If I pull my calculator back out, let's go ahead and just like yesterday, let's take the natural log of our y data. So I'll set that up in my graphing calculator. So if I take the natural log of list 2, all right, and then we'll go ahead and recreate our scatter plot, and hopefully what happens is that we get a linear set of data. So I need to change my y list to L3 since we've already transformed y. I hit zoom 9 and I should see a straight line. Wait a minute. That made things worse, didn't it? Now we've had practice with this before. What does this tell us? That this is definitely not an exponential model. We have performed the wrong type of transformation. We've actually made our data worse. Our goal is to make it more linear. Kind of looks more curved to me. So what we need to do today then is apply a new type of mathematical model. And what we're going to talk about today is what's known as a power law model. So I'm going to show you how to perform a power law transformation. We'll do the same thing we did yesterday. We'll write the line of regression, including our transformations. We'll interpret those in the context of our problem. Then we'll go through the process of evaluating our model. We'll see how well it fits, and if it fits well, we'll go ahead and make a prediction with it. All right? So pull your calculators back out. The power law model, the only difference here is instead of just transforming the y data, we're also going to transform the x data. So if we go back to our lists, we've already transformed y. We performed a natural logarithm of y. So I'm going to go into list 4, and I'm going to do the exact same thing. But now I'm going to perform a natural logarithm of my x list, L1. Now, it's going to be extremely important as we work through this problem that we keep in mind what each of our lists is representing. And if you need to, I think sometimes it's not a bad idea to just go ahead and make a little note on your piece of paper. So write down, okay, L1 is just representing x. L2 is representing y. L3 for us right now is representing the natural log of y. And L4 will be representing the natural log of x. So let's go back and recreate our scatter plot. All right, so we're going to use both transformed variables. So our transformed x right now is sitting in list 4. Our transformed y is sitting in list 3. So we're going to go ahead and set up our scatter plot in that form. We'll hit zoom 9. And now that's a much more linear set of data. All right. So again, the exponential model that we covered yesterday isn't always going to work. Our next model that we're going to look at, again, the power law. We're transforming both x and both y. So at this point, since we see a line of regression, or we see a linear form in our scatter plot, let's go ahead and apply our concepts from chapter 3. So let's create our line of regression. So we'll go stat, we choose over to calc, we choose number 8. Again, I need to set up the appropriate lists. My x list right now is list 4. My y list is list 3. So we'll go ahead and calculate that. And I'm going to slide this over so that we can interpret. We'll write the model and interpret the slope and y-intercept in the context of the problem. All right. So right now, just like yesterday, if we're going to write the line of regression, we need to include the transformations. So we're not saying...
Just conference room, please. Mr. Harden to Mr. Johnson's conference room.
All right, so back to our problem. If we're going to write the model, we need to include the transformations that we utilize. So we transform both x and y by using a natural logarithm. So let's just write that in our line of regression. So instead of saying y equals, we're going to say the natural log of y equals a plus b. Now normally we'd put in x here, but we use the natural log of x. So we need to include that as well. So again, just like yesterday, we're going to show our transformations within our line of regression. Now let's interpret those in the context of this problem. All right, for us, our a value, we need to take a note here that it's in scientific notation. So our y-intercept would be saying if the natural log of distance from the sun is 0 astronomical units, AUs, then the natural log of revolution is, now apply the scientific notation, 2.5 times 10 to the negative fourth is, so it's 0.00025. All right, again, just like yesterday, I need to include the natural logs in my interpretation. So both of the variables, both distance from the sun and our period of revolution, we applied a transformation to. The slope in this case, we'd say as the natural log of distance from the sun increases 1 AU. The natural log of revolution increases 1.5, and our unit of measure there is years, Earth years. All right? So again, just like yesterday, we're going to interpret both the slope and the y-intercept in the context of the problem, and that context also includes the transformations that we use. So you can see I'm plugging those natural logarithms into both of those interpretation statements. Now, because we've created this linear regression model, we need to evaluate it. So just like yesterday, we want to look at r squared and our residual plot. So if we look at our r squared value in this problem, up here in our calculator, this would tell us that 99% of the variation in the natural log of revolution is accounted for by the least squares regression line. Let's go ahead and create our scatter plot or our residual plot and make sure that looks appropriate as well. Again, remember, anytime I create a residual plot, the residual list is always going in the Y list. So we hit zoom 9. All right, now we've got a definite pattern here, don't we? And that doesn't look good. But again, just like yesterday, let's trace those values. And again, just like yesterday, look how small that residual is. Right? That residual is just itty bitty. And if I trace all the way through, all of those residuals are just tiny. So because the R squared value is high, because the residuals are tiny, we are willing to overlook the pattern that we see in the data. And so we'll use this mathematical model and say, yes, it is appropriate for us to represent this data using this mathematical model that we just created. Now, yesterday, we walked through how we can make prediction with our exponential model, and I want to do the same thing here. Now, just like yesterday, I want to start out with the algebra work. So we've just written this model, and we said the natural log of y is equal to a plus b natural log of x. Now, we need to apply the algebra so that we can write this into the power law form and see what that looks like. So let's do that here real quick. The first thing I'm going to do on this problem is I'm going to subtract b natural log of x from both sides. I want to get both of my natural logs on the same side. So we end up with the natural log of y minus b times the natural log of x is equal to a. Now, if you remember your properties of logarithms from your Algebra 2 or pre-calculus days, you know that we can condense this logarithmic statement into one logarithm. So the first thing I'm going to do, because this b is this constant out in front of the natural logarithm, if you remember your properties of exponents, you can remember that that b can be moved to an exponent on the x. And because we have logarithms of the same base, and we have subtraction here, all right, we can condense those down into one logarithmic statement using division. So if I apply all those properties of logarithms, what I basically end up with is the natural log of y divided by x to the b power is equal to a. Now, yesterday at this point, we applied a base of e. So we're going to do that same thing here on both sides. We apply a base of e. So the natural log and the e cancel out on the left side. We're left with y over x to the b power is equal to e to the a power. And now we're one step away. All right, we're going to multiply both sides by x to the b power. So I end up with a model y equals e to the a power times x to the b power. And that is our power law model. Now, you're going to notice, if you flip back to your notes from yesterday, that this is different than our exponential model. Our exponential model was y equals e to the a times e to the x. All right, the x was the variable. Now the x is the base, and that's the difference between an exponential model and a power law model. So let's work with this on our graphing calculator. All right, just like yesterday, we have the ability to input this into our graphing calculator. So I'm going to pull mine up here. So we're going to go into y2. All right, we're going to set y2 equal to e to the a power. Again, remember our a and b variables are in that vars menu. We'll go down to statistics. We'll go over to EQ. There's a, so I'm going to put that in. Scroll over. Then I'm going to go x to the b power, so I'm going to hit x. And then to include an exponent on our graphing calculators, we need to use this caret key, which is over above the division button. So we'll input that. That creates a little exponent box on my calculator. I'm going to access the b variable. Oops. So statistics, EQ. There's variable b, which is number 3. And so now I have this model set up in my graphing calculator. Now, yesterday, you might remember, we graphed this along with the original data. Let's do that again here and see how well things fit. So let's go back to list 1 and list 2. We knew that was curved when we first looked at it, and that's why we've gone through the transformation process. But we've created that curved model now, and again, we have that set in y2. So let's hit zoom 9. So there's our scatter plot in blue. And here comes the mathematical model we've just created. Again, look how nicely that fits with the data. That curved model is passing through all those points, and everything just looks fantastic. All right. So just like yesterday, if we want to make a prediction, let's go ahead and do that. Let's say that we went on this statistics field trip, and we were out collecting some data, and we were spending the night somewhere, and we were camping under the stars out in maybe Wyoming and Colorado, and we look up and we find what we think is a new planet. And so we find this planet and we start researching it and exploring more about it, and we find out that this planet is 50 astronomical units from the sun. So let's predict what its period of revolution is. All right? So just like yesterday, if we go back to our home screen, remember we have that y2 variable input in our calculator. So I'm going to go vars, scroll over to yvars, function, and there's y2. So I'm going to choose number 2, and we're going to plug in a distance from the sun of 50 astronomical units. So if we were 50 astronomical units away from the sun, our model predicts that our period of revolution is only 353 years. How about that? Not too shabby. So it looks like in my lifetime, I'm probably not going to see our newly discovered planet make its way around the sun, but that's all right. So that is our power law model. Now, to finish up today, I want to talk about all 3 models that we now have to use and just kind of compare some basics about them. So the first model we have back in chapter 3 is what we refer to as a linear model. And again, we just plot y versus x. And this occurs when both sets of data are changing in a linear pattern, right? They're changing by a fixed amount. And we have this linear form in our scatter plot, then our linear model is most appropriate. Yesterday, you learned about the exponential model. And in the exponential model, we only transformed the y data by applying a logarithm to it. Again, you can use a common logarithm or a natural logarithm. Either one of those is appropriate. And today, we've applied the power law model, which is when we transform both x and y. So if you look here, these are the 3 models that we're really going to focus on here in AP Stats. As we talked about last week, there are a lot of different models that we could utilize, but we don't have enough time in class to explore all of those. So AP Statistics focuses on these 2 because they are the most commonly used, the exponential and power law model. So again, if you look, linear data, just x and y, exponential log of y versus x, power law, log of y versus log of x. And that's basically kind of our tree of transformation. We assume that it's linear until we see the curved data. If we see the curved data, the first thing we'll explore is the exponential model. If that doesn't work, we'll look at a power law model. And for our purposes in this class, if none of those work, you probably made a mistake somewhere, so you'll want to go back and double check that. All right, well, hopefully that gives you a basic idea of the power law model. And so now it's time for you guys to get a little practice with it. 2 problems to look at today. Again, I'll be back tomorrow. Make sure you have the worksheet from last week where you got to practice all those different transformations. Have that ready to go. We will utilize that tomorrow. And I'll see you guys tomorrow. Have a great day. Bye.